Dear students, welcome to the lecture series on the topic Engineering Graphics. Today we are going to discuss about projections of the planes. I am Dr. IPS Ahuja, Professor, Department of Mechanical Engineering, Punjabi University, Patiala. Now here we are required to evaluate the projections of the oblique plane which happens to be inclined to the vertical plane as well as the horizontal plane. So here we have got a circular lamina having diameter, it is equal to 50 millimeter, and this circular lamina, it is resting onto the vertical plane in such a way that one of its diameters, it is inclined at an angle of 30 degree to the vertical plane and 45 degree to the horizontal plane. So we are required to evaluate the orthographic top view and the front view of this particular circular lamina. Now here we can see that this circular lamina happens to be resting onto the vertical plane and one of its diameter is inclined at an angle of 30 degree to the vertical plane. So to begin with, we are going to observe the true shape projections of the circular lamina onto the vertical plane. That is, to begin with, we are going to assume that this lamina is first of all contained by the vertical plane and thereafter the surface of the lamina will be inclined at an angle of 30 degree with respect to the vertical plane. So in the initial orthographic projections, the true shape of the lamina will be obtained onto the vertical plane in the front view projections above the XY reference line. Whereas the top view projections of this lamina, because it is contained by the vertical plane, so they will be obtained as edge view projections lying onto the XY reference line. Right? So thereafter we are going to incline the surface of this particular circular lamina at an angle of 30 degree with respect to the vertical plane. Now by virtue of the inclination of the surface of the circular lamina with respect to the vertical plane, we will see that one of the diagonals, it will be getting foreshortened because it will be getting inclined at an angle of 30 degree to the vertical plane. So this diameter, which will be inclined with respect to the vertical plane at an angle of 30 degree, will be appearing as a foreshortened distance in the front view projections over there. And now we have been provided with the information that the same diameter whose apparent length is available with us in the front view projections. So this true length of the diameter, it is further inclined at an angle of 45 degree with respect to the horizontal plane. So this angle of 45 degree with respect to the horizontal plane means that angle theta has been provided to us. Whereas in the front view projections, because of the inclination of the diameter or the surface of the circular lamina with respect to VP, we are able to observe the apparent length projections of this particular diagonal into the front view projections over there. So we are required to evaluate angle alpha. That is, angle alpha is using the principles of rotation of the line. So this angle theta, so this inclination of angle theta equal to 45 degree has to be converted to the orientation of this reduced apparent length of the diameter 17, which will be inclined with respect to VP at an angle of 30 degree. Now the apparent angle of inclination of this diameter with respect to the horizontal plane has to be evaluated. Now once we evaluate this angle alpha with respect to the horizontal plane, then we will be able to evaluate the orthographic top view and the front view projections of this particular circular lamina. Now since it is a circular lamina, there is no problem regarding the orientation of this particular circular lamina. Now let us proceed with the evaluation of the orthographic projections of this oblique circular lamina. So as we have discussed, the circular lamina happens to lie onto the vertical plane. So on the vertical plane we are going to obtain the true shape projections of this lamina. So we have got the circular projection of this lamina, that is the true shape projections of this lamina onto the vertical plane. So the front view projections will be a circular projection and it will be having the diameter, it is equal to 50 millimeter. And whatever front view projections we are able to obtain, now we have to divide this circular projection in the front view into 12 equal parts, and each segment will be equal to 30 degree. Now having obtained the front view projections, now we have to look at this particular circular lamina from the top. So as the observer is going to observe this lamina from the top, now since this circular lamina is contained by the vertical plane, so its top view projections will be the edge view projections which will be obtained onto the horizontal plane, and these projections will be obtained onto the XY reference line. So once we draw projections through these 12 points, so we find that the top view projections of all of these 12 points, they will be lying onto the XY reference line, and we can join the points 1 and 7 in order to obtain the edge view projections of the circular lamina which is contained by the vertical plane. Now we know that one of the diagonals, now you see we are talking about the diagonal 1, 7, that is in the front view it is being projected as 1 dash 7 dash, and in the top view this diagonal is represented as a true length having points 1 and 7. So distance between point 1 and point 7 happens to be 50 millimeter once again. So we know the dimensions of the edge view. Now we have to obtain the rotation of this edge view at an angle of 30 degree. Why? Because we know that this diagonal 1, 7, it is inclined at an angle of 30 degree to the vertical plane. So now we have to reorient this edge view that we have just obtained in the top view into the orientation of 30 degree with respect to the vertical plane. Now we assume that we are going to rotate the surface of this circular lamina in such a way that this lamina will be having one of its points onto the circumference, that is point number 7, resting into the vertical plane. So here we will see that we have rotated the edge view of this lamina at an angle of 30 degree in such a way that point 7, 1, it will be contained by the vertical plane, and this point 1, 1, it will be moving away from the vertical plane. So now we know the distances of all of these points with respect to 7, 1 or with respect to 1, 1. So we know this distance happens to be 50 millimeter. So distance between 1, 1 and 7, 1 happens to be 50 millimeter. Now we need to measure the distance between 7 and 8, 6, 7 and 9, 5, 7 and 10, 4, 7 and 11, 3, and 7 and 12, 2 over there. So all these points according to the distances available with us in the top view projection available as an edge view over here. So the same distance will be transformed or translated over here into the inclined projections of the edge view of this particular circular lamina. Now having obtained the top view projections of this inclined lamina with respect to the vertical plane, now the corresponding front view projections of the circular lamina need to be obtained. Now how these projections in the front view will be obtained? From all the 12 points of the plan, we have to draw vertical projectors in the upward direction, and from all the 12 points of the elevation of the previous view, we will be drawing the horizontal projectors from left to right. So wherever we obtain the intersection between the vertical projector of a particular point and the horizontal projector of the same point from the elevation view, so the intersection of the vertical projection from that point and the horizontal projector from the same point will provide us with the corresponding location of all of the points which are lying on the circumference of the circular lamina. So let us see how we are able to obtain all of these points. So here we see we have drawn vertical projectors through each of the 12 points which are available with us in the top view projections, and we are going to draw the horizontal projector from each of the points which are available with us in the front view projection, and let us find out the corresponding points of intersection between these vertical projection lines and the horizontal projection lines which we are going to draw. Now first of all, we can see that from all of these points, 12 points, we have drawn the horizontal projector lines over there. Now let us find out the intersection points which are going to be the corresponding points over here. So let us discuss each one of these points one by one. So here we can see this is the point 1, 1 dash. Point has been obtained over here by virtue of the intersection of the vertical projector drawn through the point 1, 1 and horizontal projector which has been drawn corresponding to the point 1 dash over here. Similarly, this point is 2, 1 dash. So we can check this is the vertical projector through the point 2, 1 and it is lying as an intersection with the horizontal projector which is emerging from 2 dash over here. Similarly, 3, 1 dash point has been obtained over here by virtue of the intersection of the vertical projector through 3, 1 and horizontal projector through 3 dash. Similarly, we have got 4, 1 dash obtained over here. This point 4, 1 dash has been obtained over here by virtue of intersection of the vertical projector obtained through 4, 1 and horizontal projector obtained through 4 dash. Similarly, 5, 1 dash point, it is the intersection point of the vertical projector through 5, 1 and horizontal projector through 5 dash. So similarly, 6, 1 dash, 7, 1 dash and all the other points over here, they have been obtained by virtue of intersection of the vertical projectors through point 6, 7, 8, 9, 10, 11, 12 and the horizontal projectors drawn through the same points over here. So once we obtain these 12 points, now we are going to join this and we are going to get an ellipse apparent shape projections available with us in the front view projections over here. Now into this apparent shape ellipse front view projections, so two things we have to notice. First thing is this diameter 1, 7, that is 1 dash 7 dash. So this is appearing as a foreshortened or apparent length projection of the diameter 1, 7 because this diameter 1, 7 happens to be inclined with respect to the vertical plane at an angle of 30 degree. Whereas the other diagonal, that is 4 dash 10 dash. So this is the diagonal 4 dash 10 dash. But this diagonal is still a true length. Why? Because even when we have inclined this surface of the lamina with respect to vertical plane at an angle of 30 degree, this diagonal, that is 4, 1 dash and 10, 1 dash, it is still parallel to the vertical plane. So that is why we have been able to obtain true length of this particular diagonal, right? So the diagonal 4, 1 dash, 10, 1 dash, it is the true length, whereas the diagonal 1, 1 dash and 7, 1 dash happens to be the apparent length. Now since this apparent length 1, 1 dash, 7, 1 dash, it happens to be parallel to the horizontal plane, therefore we are going to obtain 1, 1, 7, 1 as the true length diameter corresponding to this diameter. So 1, 1, 7, 1, it is the true length of the diameter which happens to be 50 millimeter. Similarly, the true length of this diameter is also 1 dash and 7 dash. And here again we have got the true length of this diameter as 1 and 7 distance over here. Now we know that the diameter which was previously inclined at an angle of 30 degree with respect to VP, that is diagonal 1, 7. So the same diagonal true length, it is further inclined at an angle of 45 degree with respect to the horizontal plane. Now we can check that we have to rotate, transform this apparent shape elevation projection over here into the new orientation. But over here we observe that this apparent length 1 1 dash and 7 1 dash. So this is the apparent length, whereas the angle of inclination, that is angle theta, so that is given to us. This is with respect to the true length of the diameter. So here we have got apparent length to be transformed, but we have been provided with the orientation of the true length of the diameter to be equal to how much? 45 degree. So now you can check, theta orientation is always with respect to the true length of the edge or true length of the dimension over there. Now the true length of the dimension is how much? We can check. It is equal to 1 dash 7 dash, it is equal to 1 7, or it is equal to 1 1 and 7 1. So all of these three dimensions, they happen to be 50 millimeter. So once we know this dimension of true length is 50, what we are going to do? This distance we are going to mark as 50 millimeter. So we are going to mark 2 points over here, and the distance between these 2 points will be equal to 50 millimeter. So once we mark these 2 points, let us label those points. One point we have labeled as 7 2 dash, another point we have labeled as 1 2 1 dash, because true length is always having an additional suffix over there. So now this is the true length of the diagonal 1 7, represented as true length in the front view projections over here. So this is 1 2 1 dash and 7 2 dash. So we know that from the principles of the rotation of the line, whenever we have got the location of the two endpoints of a true length, between these two, you see locus line. One locus line is over here, another locus line is over here. So between these two locus lines, we are also going to obtain the apparent length projections of this line. So between these two locus lines, our apparent length will also be line as per the principles of the rotation of the line. So how much is the apparent length? So here we have got the measurement of the apparent length. So we are going to measure this length, that is 1 1 dash and 7 1 dash. So the distance between these 2 points we are going to measure. And once we measure this distance, so now we'll keep our needle point over here. Open compass is equal to 7 1 dash 1 1 dash, and mark an arc onto this locus line. So wherever we are able to mark this arc, so we'll be able to find out the location of this point, and the name of this point will be 1 2 dash. So this is the apparent length. So 1 2 dash and 7 2 dash. So this is the new orientation or new inclination of this apparent length, which is available with us in the front view projections. So the moment we are able to mark the location of the apparent length, now we can measure the angle of inclination. So the angle of inclination is 49 degree. So we know that the apparent length in elevation, it is inclined at an angle of 49 degree. And we know that true length will be greater than the apparent length, and the apparent angle of inclination alpha, it will be greater than the true angle of inclination, that is theta. So alpha, it is greater than theta, whereas true length, it is greater than the apparent length. Now once we mark this apparent length of the line, now once again using the rectilinear distances, we will be able to transfer this ellipse from this orientation to another orientation, and this another orientation is such that the apparent length of the diagonal, which one is this diagonal? 1 2 dash and 7 2 dash. So this is the new diagonal basically. So into this orientation, the apparent length of the diagonal in the front view will be inclined at an angle of 49 degree with respect to the horizontal plane. Now how do we shift this figure over here? So very easy. So please check. Here we have got point 1 1 dash. Here we have got 7 1 dash. So here these 2 points have been translated over here. 1 2 dash and 7 2 dash. So this length is already available with us. Now what we are going to do? From 1 1 dash we will be measuring these 5 distances. 1 2 2, 3, 4 and 5. So these 5 points, distance of these 5 points from 1, 1 dash we are going to measure. So please see point 1, point 2, point 3, point 4 and point 5. So these 5 points we are going to mark from this point 1, point 2, point 3, point 4, point 5. Now from point 1, this distance vertical and this distance vertical is equal. So we'll measure this distance and this. Similarly, from the point number 5, same distance will be there, which is going to define points 6 and 8 over here. This distance will be defining 4 points, 2, 12, 6 and 8. So from point 1, we'll mark the same distance. So points 2, 2 dash and 12, 2 dash will be located. Same distances we have to mark from point number 5. This one and this one. So another 2 points 6 and 8, that is 6, 2 dash and 8, 2 dash will be located. Similarly, from points 2 and 4 over here. Now this vertical distance I need to measure. So this distance, it is equal to this distance, it is equal to this distance and it is equal to this distance. So if we measure this distance, now corresponding to points 2 and 4, 4 points we will be able to locate. Which are the 4 points? 3, 11, 5 and 9. So please check. We are going to measure the point number 2nd distance, and now from here, this distance we are going to drop in the perpendicular direction above and below. So this distance is above, define point 11. This distance we draw below, define point number 3. And similarly 1, 2, 3, 4. So from the 4th point, measure the same distance in the upward direction perpendicular. Point number 9 will be defined. Measure the same distance below this particular center line. So point number 5 will be defined. And finally point 1, point 2, point 3. So this is point 3. This is also point 3. So from point 3 in the perpendicular direction, measure this distance, that is define point 10, and measure this distance, it is equal. Define point number 4. So from point number 3, draw this distance, same one as this one, and draw it in the downward. Same distance upward, same distance downward. So we can define 4, 2 dash and 10, 2 dash. So this way, all the 12 points of the front view will be defined and we can join all these points. So this way, we have been able to transfer ellipse apparent length projections of the circular lamina which we had obtained in the front view projections previously. So only thing is, we have been able to reorient the position of this apparent shape ellipse in such a way that this diagonal 1, 1 dash and 7, 1 dash, it has been reoriented at an angle of 49 degree over here. Now having obtained the front view apparent length projections corresponding to the oblique circular lamina, now the corresponding points in the top view we are going to obtain. So again, the same methodology we are going to use. From these 12 points, we are going to draw the vertical projector lines. From these 12 points of the plan, we are going to draw the horizontal projector lines. So wherever from the elevation projection points, the vertical projectors, they are going to intersect with the horizontal projectors of the corresponding points. So the 12 points of the plan projection view of the oblique lamina will be obtained over here. So let us see how we can obtain all of these 12 points. So please check. Here we have drawn the horizontal projectors from all the 12 points of the plan projection view which we had obtained previously. Now, one by one, we are going to obtain vertical projectors from all of these 12 points. And let us see the corresponding points of intersection between the vertical projector lines and the corresponding horizontal projector lines corresponding to the same point. So here we can see from point 1, 2 dash. So a vertical projector has been drawn over here. This will be projected until it intersects with the horizontal projector which has been drawn through the point 1, 1 over here. So we obtain point number 1, 2 in the plan. Similarly, this is point 2, 2 dash. So we draw a vertical projector. We are going to extend this projector till it intersects with, you can see this point is 12 and 2. So from 2, 1 of the plan, a horizontal projector will be drawn over here. So wherever this horizontal projector through point 2 in the plan, it intersects with the vertical projector from the point 2 in the elevation. So point number 2, 2 will be obtained. Similarly, this is the location of point 32. So this point 32 has been obtained by virtue of the intersection of vertical projector from 32 dash and horizontal projector from 31 over here. Right, so this is point 32. So similarly, point 42. So here we get vertical projector from 42 dash, and this is the horizontal projector from 41. So this intersection point will yield us the location of point 42 over here. So similarly, point 52 has been located over here by virtue of the intersection of vertical projector from point 52 dash and horizontal projector from 51. So here we have got location of point 62. Again, we have drawn vertical projector from 62 dash and horizontal projector from 61. So this is point 61 over here, right? This is horizontal projector of 61. So this intersection provides us with the point 62. And next, this is vertical projector from 72 dash, which we have drawn. Now here is horizontal projector from point 71. So wherever this vertical projector and this horizontal projector they intersect, we obtain the point 72 over here. Next, we have got vertical projector from 82 dash. So as we move down, so we find that this vertical projector, it is going to intersect with horizontal projector drawn through the point 81. This is the point 81 over here. Next, you have 92 dash over here. So from 92 dash, again we have drawn a vertical projector line, and wherever it intersects with horizontal projector drawn through 91, point 92 is obtained. So this is point 102. So this is the intersection point corresponding to the vertical projector from 102 dash and the horizontal projector from 101 over here. And next you have got point number 11. So here you can see this is point 11 2. So this is obtained by virtue of intersection of vertical projector drawn through the point 11 2 dash and the horizontal projector which is drawn through the point 11 1 over here. And finally, this is point number 12, this one, right? So this point is point number 12. From point number 12 2 dash, now we will be drawing a vertical projector downwards, and from point 12 1, a horizontal projector has been drawn. So wherever these two projectors they intersect, so we have obtained the point of intersection as 12 2 over here. So this way all the 12 points in the top view projections they have been obtained. And once we join all of these 12 points, so we have been able to obtain the top view projections of this oblique lamina, which is inclined with respect to vertical plane at an angle of 30 degree and with respect to horizontal plane at an angle of 49 degree. So this way we have been able to obtain orthographic projections of an oblique circular lamina which happen to be inclined to the vertical plane at an angle of 30 degree, and the apparent length diagonal of this particular circular lamina, it is inclined at an angle of 49 degree, or we can say the true length projection of this lamina in the front view, it is inclined at an angle of 45 degree. So this is all for today. So I hope that through this discussion you would have been able to understand about the procedure to evaluate the orthographic projection of an oblique circular lamina which happens to be inclined with respect to vertical plane as well as the horizontal plane. So we are going to continue with further discussion regarding few more illustrative cases of orthographic projections of the oblique planes in the coming lectures. So thank you very much. Thanks a lot.